Let's move now to the last part of this lecture, focusing on bugs and how they can be exploited by adversaries. In this case, we will focus on a specific type of attack, the buffer overflow attack. Before focusing on buffer overflow attacks, let me focus on some general considerations. It should be clear that cracking a password is only one way to gain control from the attacker's perspective. There can be alternative ways, which even require fewer efforts in some cases. One of them is to manage to trick the user into doing something that will harm him or her. And this could be done by infecting the browser, have users download malicious content, and so on. The other is to exploit bugs, which are definitely there in operating systems. Let's focus now on buffer overflow attacks. First, we need to know that the C programming language does not perform array bounds check. If we want to be sure we do not write in an array, a buffer of characters, for instance, something that is larger than the array itself, we need to do that explicitly. Second, we need to remember that the stack of a process grows downwards from the last address to smaller ones. Let's see now what is happening. When we jump from the main function to a different function, we need to keep track of where we were so that we can get back there once the function has completed its execution. We do this by writing a return address. After such a return address, we will have the various variables used by the function, A in the example. Among these, we can have a buffer B. If a malicious user is aware of this and also has the chance of giving back to the procedure A what should be written inside B, then it can give a longer input. This input can override the return address. In this case, the attacker can put a predefined value there, even pointing to an address within the input he or she just provided. The code available there would then be executed next. It turns out some system calls from the operating system suffer from this bug. If the return address is changed to point to an injected code that starts a terminal, a malicious user can have access with full privileges to the computer because the system call was being run by the operating system itself. A way to detect possible attacks that is not 100% secure is to use stack canaries. In this case, just below the return address, we can add a random value and compile programs with special code that will stop the execution if such value is changed. The idea is that when overflowing the buffer, the attacker will also change such random value, and the program will be able to detect this. As I mentioned in the slide, you can check in the book how stack canaries can be avoided. Alternative ways to go include the no execute bit, which in this case is based on the hardware itself and used to specify portions of memory that cannot contain executable parts. In this case, it is possible to prevent code injection attacks because no code will be executed.